So, today I am going to talk about permutations. So, the usual standard definition of permutations is a permutation on n letters is a bijection sigma from the set. Remember, this box n denotes the set of numbers from 1 to n, sigma from n to n. There is a very nice definition which is equivalent to this in Knut's book, The Art of Computer Programming. So, in the Art of Computer Programming in volume 3, Knut devotes an entire chapter to permutations, and the reason being that, as we shall also see, permutations play an important role in sorting algorithms in computer science. So, Knut's definition I rather like. It says that a permutation is an arrangement of the elements of n. So, a permutation on n letters is an arrangement of the elements of n in a row. These are basically equivalent, but the second one we will see is nice to work with. So, what is the relation between these two definitions? Well, if you have a bijection from n to n, then you can write down sigma 1, sigma 2, sigma n, the values of this bijection at 1, the value of sigma at 2, the value of sigma at n. And each element from 1 to n will occur exactly once in this, and so this is really an arrangement of the elements of the set 1 to n in a row. And conversely, if you have an arrangement of the elements of 1 to n in a row, let us say we have an arrangement a 1, a 2, a n, then you can just define sigma I to be a I, and that will give you a permutation. So, we can go back and forth between these two different definitions of a permutation, which but I will mostly be using the second viewpoint due to Knut. I will use the notation perm n to denote the set of all permutations on n letters. And typically given a permutation sigma, I will write down the arrangement that corresponds to it as a1, a2, an. This is sometimes called the one line notation for a permutation. Let us look at an example. So, what are the permutations of 3 letters? So, what we have to do is we have to take the numbers 1, 2, 3 and we have to arrange them in a row in all possible ways. So, let us see what are the different ways of arranging 1, 2, 3 in a row. Well, you can arrange them simply in increasing order, or what you could do is if you want to start with a 1, you could interchange 2 and 3. So, 1, 3, 2. Well, that takes care of all the permutations of 3 letters which begin with 1. Now, let us look at the ones which begin with 2. Well, the remaining letters are 1 and 3. So, we can either write 2, 1, 3 or 2, 3, 1, and then if we start with 3, we have 3, 1, 2 and 3, 2, 1. So, what we see is that there are 6 permutations of 3. The cardinality of perm 3 is 6. Okay. Now, a fundamental feature of a permutation is an inversion. So, let me define an inversion. An inversion of a permutation sigma, which I will write in one line notation as A1 AN. So, this is a permutation on n letters, is a pair AI comma AJ, where such that I is less than j, but AI is greater than AJ. In other words, an inversion is a pair in the arrangement that is out of order. Even though AI is greater than AJ, it appears before AI in the arrangement. Let us look at a simple example. Let us look at the permutation 3, 1, 4, 2. So, this is in perm 4, it is a permutation on 4 letters. What are the inversions? So, 3 comma 1 is an inversion because 3 comes before 1, 3 appears to the left of 1. 3 comma 4 is not an inversion because 3 is less than 4. So, it is not a pair that is out of order. 3 comma 2, well, that again is a pair that is out of order. So, that is an inversion. 1 comma 4 is not an inversion, 1 comma 2 is not an inversion, but 4 comma 2 is an inversion. So, this permutation 3 1 4 2, this has 3 inversions. And we will define the inversion number of a permutation. We will call it inv of sigma. This is the number of pairs. So, we assume that sigma is a permutation of n letters. Then we look at the number of pairs I less than j that lie between 1 and n, but AI is greater than AJ. This is called the inversion number of the permutation sigma. So, the inversion number of 3 1 4 2 is 3. We can keep track of the inversions more carefully, and this is done by the means of an inversion table. So, given sigma equals A1, A2, AN, its inversion table is the sequence B1, B2, Bn, where Bj is the number of elements of n to the left of j that are actually greater than j. Let us look at an example. So, let us take a slightly larger permutation this time, so that we have somehow it is more interesting. So, let us take sigma to be a permutation of 9 letters 5, 9, 1, 8, 2, 6, 4, 7, 3. So, this has 9 letters. This is an arrangement of the numbers 1 to 9 in a row. And let us see what its inversion table is. Okay, so what is B1? So let us look at the definition. The number of elements to the left of 1. So where is 1? Here is 1, and we are looking at the number of elements to the left of 1 that are greater than 1. So now if you look at the elements that are to the left of 1, there are 2 of them, 5 and 9, both of them are greater than 1. So B1 is 2. So let us write that down. B1 is 2. Okay, what about B2? So the number of elements to the left of 2 that are greater than 2. Now there are 4 elements to the left of 2, 3 of them are greater than 2. So B2 is 3. B3, well, the number of elements that are to the left of 3 and greater than 3. Well, so 1, 5, 9, 8, 6, 4 and 7. So that is 5, 9, so 1, 2, 3, 4, 5, 6. So there are 6, B3 is 6. B4 is 1, 2, 3, 4. B5 is, well, 5 is right up in front. So B5 is 0. B6, well, there is 9 and 8. So that is just 2. B7, well, there is 8 and 9, that is again 2. B8, well, that is 1 and 0. So this is the inversion table 2, 3, 6, 4, 0, 2, 2, 1, 0. An interesting thing about the inversion table is that you can recover the permutation from the inversion table. So let us just copy out only this inversion table on a new page and see if we can recover the permutation from the inversion table. So here is my inversion table. Can I reconstruct the permutation from this inversion table? So the trick is to start with, okay, so we know that this inversion table is of length 9. So this must be a permutation on 9 letters, right. So and we know that 9 occurs somewhere in it. I do not know exactly where in the permutation, but let us just write 9 down. So it occurs somewhere. So we will reconstruct it by putting the numbers down in reverse order. Okay. So now look at this. So let me write down, what numbers these correspond to. This is B1, this is B2, this is B3, B4, B5, B6, B7, B8, B9. Now what about 8? So the question is, does 8 occur to the left of 9 or to the right of 9? Well, look, B8 has value 1. So that means that there is one number greater than 8 which occurs to its left. Now the only possibility is 9. So 8 must occur to the right of 9. So I will write 8 over here. I will leave some space in between because who knows, other numbers might appear in between. Okay, what about 7? So 2 numbers larger than 7 appear to the left of 7. Now the only numbers larger than 7 are already over here, 9 and 8. So 7 must be further to the right. Okay, so I will leave some space and write 7 over here. What about 6? Okay, 2 numbers larger than 6 appear to its left. So 6 must be between 8 and 7, right. So I think you are getting the idea now. What about 5? Well, no numbers larger than 5 appear to its left. So 5 must be to the left of all these numbers. What about 6? No, sorry, where were we? What about 4? 4 numbers larger than 4 appear to the left of 4. So 1, 2, 3, 4, 4 must be somewhere between 6 and 7. And then let us look at 3. There are 6 numbers to the left of 3. So 1, 2, 3, 4, 5, 6. 3 must be all the way at the end. And then 2, there are 3 numbers to the left of 2 which are greater than 2. So 2 must be in between, and there are 2 numbers greater than 1 to the left of 1. So 1 must be here, and so what we get is sigma is equal to 5, 9, 1, 2, 8, 6, 4, 7, 3. Let us check. 591826473. Now, what this is saying is that from a permutation I can construct an inversion table, and also given an inversion table I can recover the permutation. But what are the possible inversion tables that you can actually have? So, obviously we have that okay, so let us look at B1. What are the possible values it can take? Right. So, B1 is the number of elements of 1 to n that are greater than 1 and lie to the left of 1. So, it is possible that 1 is at the very beginning of your permutation, in which case B1 would be 0. The other extreme is that 1 is at the right of your permutation, which means B1 would be 8, right. So, in this case B1 could be anything between 0 and 8. In general, if you have a permutation of n, B1 lies between 0 and n minus 1. What about B2? Well, there are n minus 2 numbers that are greater than B2. So, B2 again could lie between 0 and n minus 2. B3 could be any number between 0 and n minus 3. In general, what we have is Bi lies between n minus I and 0, and an interesting case is that of Bn. So, what is Bn? It is the number of elements of the set 1 to n which are greater than n and lie to the left of n, but nothing is greater than n in the set 1 to n. So, Bn lies between 0 and 0, which is consistent with this formula n minus n, right. And given a sequence like this, given a sequence of numbers B1, B2, B3 such that Bi is less than or equal to lies between 0 and n minus I, you can take this algorithm and reconstruct a permutation with exactly that sequence as its inversion table. Okay, so, what we have shown is that permutations are in bijective correspondence with inversion tables. So, let me just write that down, maybe we can call it a theorem. The function taking each sigma in perm n to its inversion table gives a bijection from the set of all permutations onto the set of all possible inversion tables. So, permutations n to the set of all possible inversion tables. So, what is the possible set for B1? So, let me introduce some notation. So, what I am saying is that Bi belongs to okay. So, it lies between 0 and n minus I. So, what notation I am using here is to say that 0 comma k is just the set of integers 0, 1, 2, k. Normally when we use box k, it is from 1 to k. So, I need to distinguish between that and this. So, here it is 0 to k. This is not to be confused with the closed interval notation that we will be using later. Exactly the same notation we will be using for closed intervals later on. This is just the integers that lie between 0 and k. So, what we get is permutations are in bijection with. So, now B1 lies between 0 to n minus 1, B2 lies between 0 to n minus 2, all the way down to Bn, which lies between 0 and 0. That is last one is a singleton set consisting only of 0. And a nice corollary of this is that the number of permutations of n is, well, the cardinality of this set, which is n, the cardinality of 0 to n minus 2, which is n minus 1, all the way down to this is our n factorial. I am sure you already knew this fact, but this is a nice slightly different proof.